In the silent depths of the night sky lies a tapestry of light that stretches beyond our imagination. Countless galaxies, each containing billions of stars, float like islands in the cosmic ocean. The vastness of space presents us with one of humanity's greatest intellectual challenges. How do we measure the distances to objects so far away that light itself takes millions or billions of years to reach us? When we gaze upward on a clear night, we see stars that appear as mere points of light, seemingly arranged on a flat celestial dome. Yet, this is an illusion. The universe exists in 3 dimensions, with stars and galaxies scattered at profoundly different distances from Earth. Understanding these distances is not merely an academic exercise, but the foundation upon which our entire understanding of the cosmos rests. The scale of the universe is difficult for the human mind to comprehend. If we were to reduce our sun to the size of a grain of sand, the nearest star would be another grain of sand over 4 kilometers away. On this scale, our entire Milky Way galaxy would span the North American continent. And beyond our galaxy lie billions more, separated by voids of intergalactic space so vast that light, traveling at 300,000 kilometers per second, requires millions of years to cross them. For most of human history, these distances remained unmeasurable. Ancient astronomers could chart the positions of celestial bodies with remarkable precision, but they had no reliable way to determine how far away they were. It was not until the 19th and 20th centuries that astronomers developed techniques sophisticated enough to begin mapping the 3-dimensional structure of our cosmic neighborhood. Today, measuring cosmic distances remains one of astronomy's most fundamental challenges. It is also one of its most crucial endeavors. Without accurate distance measurements, we cannot determine the true physical properties of distant objects, the age of the universe, or even its ultimate fate. Distance is the key that unlocks our understanding of cosmic history and structure. The methods astronomers use to measure these vast distances form what we call the cosmic distance ladder, a series of techniques that build upon one another, each rung allowing us to reach farther into the universe. From the nearby to the unimaginably distant, these methods reveal a universe of staggering proportions, one that continues to expand in ways that challenge our deepest intuitions about space and time. As we embark on this journey through astronomical measurement, we invite you to consider not just the technical aspects of how we measure cosmic distances, but also what these measurements tell us about our place in the universe. For in learning how astronomers map the cosmos, we also learn something profound about ourselves. A species of cosmic explorers who have learned to measure the immeasurable and comprehend the incomprehensible. In the quiet hours of the night, as the stars wheel overhead, let us contemplate how human ingenuity has allowed us to reach across the light years and touch, if only with our understanding, the most distant shores of the cosmic ocean. Our journey into cosmic measurement begins with perhaps the most intuitive method astronomers use to determine distances, a technique known as parallax. This method relies on a simple phenomenon that you can demonstrate right now, wherever you are. Hold up your thumb at arm's length and look at it with one eye closed, noting its position against the background. Now switch eyes, closing the one that was open and opening the one that was closed. You will notice that your thumb appears to shift position relative to more distant objects. This apparent shift in position when viewed from different vantage points is what we call parallax. This same principle operates on a cosmic scale. As Earth orbits the Sun, our vantage point shifts by approximately 300 million kilometers over 6 months. This change in perspective causes nearby stars to appear to move slightly against the background of more distant stars. By measuring this tiny shift, astronomers can determine the distance to stars within our galactic neighborhood using simple geometric principles. The concept of stellar parallax dates back to ancient times. The Greek astronomer Hipparchus recognized in the 2nd century BCE that if Earth orbited the Sun, we should be able to detect parallax shifts in the positions of stars. However, These shifts proved too small to measure with the naked eye, or even the earliest telescopes. The absence of detectable stellar parallax was, in fact, one of the principal arguments against the heliocentric model of the solar system for centuries. It was not until 1838 that the first successful measurement of stellar parallax was achieved by Friedrich Wilhelm Bessel. Using a precision instrument called a heliometer at the Königsberg Observatory, Bessel measured the parallax of 61 Cygni, a binary star system about 11 light-years from Earth. The angle of shift he measured was tiny, less than 1 arcsecond, which is equivalent to the width of a human hair viewed from 20 meters away. This achievement marked a watershed moment in astronomy, providing the first direct measurement of the distance to a star beyond our Sun. The formula used to calculate distance from parallax is elegantly simple. The distance to a star in parsecs equals 1 divided by the parallax angle measured in arcseconds. This gives us a natural astronomical unit of distance called the parsec, which equals about 3.26 light-years. A star with a parallax of 1 arcsecond would be 1 parsec away, while a star with a parallax of half an arcsecond would be 2 parsecs away. The smaller the parallax angle, the more distant the star. For the first time in human history, astronomers could measure cosmic distances directly, without resorting to assumptions or theoretical models. This opened the door to understanding the true scale of our stellar neighborhood and eventually the broader universe beyond. Ground-based parallax measurements remained limited in both accuracy and range throughout the 19th and most of the 20th centuries. Even the best observations could only reliably measure stars within about 100 parsecs of Earth, a tiny fraction of our Milky Way galaxy. The atmosphere blurs starlight just enough to make measuring the minute angles involved exceptionally difficult from the ground. The parallax technique received a dramatic boost with the launch of the European Space Agency's Hipparcos satellite in 1989. Operating above Earth's atmosphere, Hipparcos measured the parallaxes of more than 100,000 stars with unprecedented precision, extending reliable distance measurements to roughly 1,000 parsecs. But the true revolution came with the Gaia mission, launched in 2013. This remarkable space observatory has measured the positions, motions, and parallaxes of nearly 2 billion stars across our galaxy with astonishing precision. Gaia can detect parallax shifts as small as 20 microarcseconds, equivalent to the width of a human hair, as seen from 2,000 kilometers away. This has allowed astronomers to directly measure distances to stars up to 30,000 light-years away, encompassing a significant portion of our Milky Way galaxy. The technical challenges involved in these measurements are formidable. Detecting such minute angular shifts requires extraordinary precision in both the telescope optics and the positional measurements. Gaia achieves this through a combination of innovative engineering and sophisticated data processing. The spacecraft actually contains 2 telescopes that observe simultaneously, with their fields of view separated by a precisely maintained angle. As the spacecraft slowly rotates, it repeatedly scans the entire sky, building up observations of each star from multiple angles over time. This allows astronomers to average out random errors and achieve unprecedented positional accuracy. Despite its power, parallax has fundamental limitations. The farther away a star is, the smaller its parallax angle becomes, eventually becoming too tiny to measure even with our best instruments. At the distances of other galaxies, millions or billions of light-years away, the parallax effect becomes vanishingly small, well beyond our current technological capabilities to detect. For objects beyond our galaxy, astronomers must turn to other methods. Nevertheless, parallax serves as the essential first rung of the cosmic distance ladder. It provides the calibration for all other distance measurement techniques. Without accurate parallax measurements of nearby stars, astronomers would lack the foundation necessary to extend distance measurements to the farthest reaches of the observable universe. The significance of parallax extends beyond mere distance measurement. By determining the distances to stars, astronomers can convert apparent brightness to absolute brightness or luminosity. This reveals the true physical properties of stars, allowing us to understand their sizes, temperatures, and evolutionary states. Combined with spectroscopic data, which reveals chemical compositions, parallax-based distances help astronomers construct detailed models of stellar evolution and galactic structure. Consider the practical applications of this knowledge. When astronomers discover a star similar to our Sun in terms of mass, age, and composition, accurate distance measurements allow them to determine whether any planets orbiting that star might potentially harbor conditions suitable for life as we know it. The search for habitable worlds beyond our solar system depends critically on our ability to measure stellar distances precisely. Parallax also helps astronomers map the three-dimensional structure of our galaxy. By combining distance measurements with positional data, they can trace the spiral arms of the Milky Way, identify star clusters, and chart the distribution of interstellar dust and gas. This structural information provides crucial insights into galactic evolution and star formation processes. The story of parallax measurement illustrates a recurring theme in the history of astronomy: the synergy between theoretical understanding and technological innovation. The concept of parallax had been understood for centuries, but only when technology advanced sufficiently could its potential for cosmic measurement be realized. This pattern repeats throughout astronomical history, from Galileo's first telescopic observations to today's space-based observatories and massive ground-based instruments. As we lie beneath the night sky, contemplating the stars scattered across the darkness, we can now appreciate that what appears as a two-dimensional canvas is in reality a scene of extraordinary depth. The stars we see are scattered through space at vastly different distances, from the relatively nearby Proxima Centauri, just 4.2 light-years away, to distant giants visible to the naked eye despite being hundreds or thousands of light-years distant. And yet, for all its power, parallax reveals only our immediate cosmic neighborhood. To venture beyond, to measure the distances to other galaxies, and eventually to the edge of the observable universe, astronomers needed to develop additional techniques. The next rung on the cosmic distance ladder involves special types of stars, whose intrinsic properties allow them to serve as standard candles, cosmic lighthouses, whose true brightness is known or can be determined. As our understanding of cosmic distances has expanded, so too has our sense of humility. We occupy a small planet, orbiting an ordinary star in one galaxy among billions. Yet through careful observation and mathematical insight, we have learned to measure distances so vast that they challenge our comprehension. In this way, astronomy connects us to the cosmos and reminds us of both our insignificance and our remarkable capacity to understand the universe of which we are a part. As we venture beyond the reaches of parallax measurement, we enter a realm where the vast distances between galaxies require new methods of cosmic cartography. Here, astronomers turn to what they call standard candles, objects whose intrinsic brightness is either constant or can be determined through other observable properties. Among these cosmic lighthouses, none have been more historically significant than a special class of stars known as Cepheid variables. Cepheid variables are massive luminous stars that exhibit a fascinating property. Their brightness does not remain constant, but instead pulsates with remarkable regularity, growing brighter and dimmer in cycles that can last from 1 to 100 days. These stellar pulsations occur because Cepheids exist in a state of delicate balance. The outer layers of the star expand and contract rhythmically, like the breathing of a cosmic giant. The physics behind these pulsations relates to the way energy moves through the star. Within a Cepheid, a zone of partially ionized helium acts as a valve for the outward flow of energy. When compressed, this zone becomes more opaque, trapping energy and causing the star to expand. As it expands, the zone becomes more transparent, allowing energy to escape and causing the star to contract once again. This cycle repeats with clockwork precision, creating the regular brightness variations that define Cepheid variables. The key to their usefulness in distance measurement was discovered by a remarkable astronomer named Henrietta Swan Leavitt in the early 20th century. Working at Harvard College Observatory as one of the human computers employed to analyze astronomical data, Leavitt was tasked with cataloging variable stars in the Small Magellanic Cloud, a satellite galaxy of our Milky Way. In 1908, she made an observation that would transform our understanding of the universe. Leavitt noticed that among the Cepheid variables she was studying, there appeared to be a relationship between two properties, the period of their pulsation and their apparent brightness. Stars with longer pulsation periods consistently appeared brighter than those with shorter periods. Since all the stars in the Small Magellanic Cloud are roughly the same distance from Earth, Leavitt realized that this relationship must reflect the star's intrinsic brightness, not just how bright they appear to us. This discovery, now known as the period-luminosity relation, was revolutionary. It meant that by simply measuring how long it takes a Cepheid to complete one cycle of pulsation, astronomers could determine its true luminosity. By comparing this intrinsic brightness with how bright the star appears from Earth, they could then calculate its distance using the inverse square law of light propagation, which states that apparent brightness diminishes with the square of distance. The implications were profound. For the first time, astronomers had a method to measure distances far beyond the limits of parallax. If they could identify Cepheid variables in other galaxies, they could determine how far away those galaxies were. This opened the door to mapping the universe on an entirely new scale. The potential of Cepheids as distance indicators was first fully realized by Edwin Hubble in the 1920s. Using the 100-inch Hooker telescope at Mount Wilson Observatory, then the largest telescope in the world, Hubble identified Cepheid variables in what was then known as the Andromeda Nebula. By applying Leavitt's period-luminosity relation, he calculated that Andromeda was approximately 900,000 light-years away, far beyond the boundaries of the Milky Way. This measurement definitively proved that Andromeda was not a nebula within our galaxy, as many astronomers had believed, but an entirely separate galaxy. At a stroke, the known universe expanded from a single galaxy to a cosmos filled with countless island universes, each containing billions of stars. Hubble's work, using Cepheid variables as distance indicators, transformed our cosmic perspective forever. Over the decades, the Cepheid method has been refined and calibrated with increasing precision. We now know that there are actually two distinct types of Cepheid variables, Type 1 or classical Cepheids, which are relatively young, massive stars, and Type 2 Cepheids, which are older, less massive stars. Each type follows a slightly different period-luminosity relation, and distinguishing between them is crucial for accurate distance measurements. The challenge in using Cepheids lies in their identification and observation. To find a Cepheid variable, astronomers must take multiple images of the same region of sky over an extended period, looking for stars that change in brightness with the characteristic pattern of Cepheids. Once identified, the pulsation period must be measured precisely, requiring observations spanning several cycles. For a Cepheid with a 30-day period, this might mean monitoring the star for months. Furthermore, the light from distant Cepheids must traverse vast clouds of interstellar and intergalactic dust, which can absorb and scatter certain wavelengths more than others, effectively dimming and reddening the starlight. Astronomers must carefully correct for this interstellar extinction to avoid underestimating distances. This requires observations across multiple wavelengths, typically in the visible and infrared portions of the spectrum. The launch of the Hubble Space Telescope in 1990 marked a new era in Cepheid observations. Operating above Earth's atmosphere, Hubble could detect Cepheids in galaxies up to 100 million light-years away, vastly extending the range of direct distance measurements. The telescope's key project on the extragalactic distance scale, completed in 2001, use Cepheid variables to calibrate other distance indicators and determine the Hubble constant, which describes the rate of cosmic expansion. More recently, the development of infrared observing capabilities has further enhanced the utility of Cepheids. Infrared light penetrates dust more effectively than visible light, allowing for more accurate measurements in dusty regions. The Spitzer Space Telescope and now the James Webb Space Telescope have taken advantage of this property to refine Cepheid distance measurements even further. Despite their tremendous value, Cepheid variables have limitations as distance indicators. They are relatively rare stars, and only the brightest are visible in distant galaxies. Even with our most powerful telescopes, we cannot detect individual Cepheids in galaxies beyond about 100 million light-years, a small fraction of the observable universe, which extends roughly 46 billion light-years in all directions. Additionally, the period luminosity relation must be calibrated using Cepheids, whose distances are known through independent means, such as parallax. Any errors in this calibration propagate through all Cepheid-based distance measurements. Indeed, one of the most pressing problems in modern cosmology, the Hubble tension, relates to discrepancies between different methods of measuring cosmic distances and expansion rates, with Cepheid calibration playing a central role in the debate. Nevertheless, Cepheid variables remain one of the most reliable rungs on the cosmic distance ladder. They bridge the gap between the relatively nearby stars whose distances we can measure directly through parallax and the far more distant galaxies, whose distances must be determined through other means. Without Cepheids, our map of the cosmos would be far less complete, and our understanding of cosmic evolution far more limited. The story of Cepheid variables reminds us that astronomical discovery often depends on patient, meticulous observation. Henrietta Swan Leavitt examined thousands of photographic plates to identify the period-luminosity relation. Edwin Hubble spent countless nights at the telescope to find Cepheids in Andromeda. Today's astronomers continue this tradition, using increasingly sophisticated instruments but still relying on the same fundamental approach: careful observation of celestial patterns revealed over time. As we contemplate these pulsating stars, we might reflect on how their rhythmic variations, like cosmic heartbeats, have helped us measure the enormity of space. Each Cepheid carries within its regular cycle the key to determining distances so vast that light itself requires millions of years to traverse them. Through these stellar beacons, we have extended our cosmic vision far beyond what our ancestors could have imagined. But even Cepheids cannot carry us to the farthest reaches of the observable universe. For that journey, astronomers needed to find even brighter cosmic lighthouses, standard candles so luminous that they could be seen across billions of light years. These would be found in the most catastrophic stellar events known, the explosions of stars in what we call supernovae. In these brilliant cosmic deaths, astronomers would discover the next crucial rung on the cosmic distance ladder, extending our reach toward the very edge of the observable universe. While Cepheid variables opened the door to measuring distances to nearby galaxies, astronomers needed even brighter cosmic beacons to probe the deeper reaches of space. These would come in the form of stellar explosions so powerful they can briefly outshine entire galaxies, events we call supernovae. Among these cataclysmic explosions, one particular type has emerged as an invaluable tool for cosmic cartography: Type Ia supernovae. Type Ia supernovae represent the dramatic end of a binary star system's life story. Unlike other supernovae that result from the collapse of massive stars, Type Ia supernovae occur in systems where a white dwarf, the dense remnant of a sun-like star, orbits in close proximity to a companion star. Over time, the white dwarf's powerful gravity pulls material from its companion. As this stellar material accumulates on the white dwarf's surface, the pressure and temperature at its core steadily increase. What makes Type Ia supernovae so useful for distance measurement is the remarkably consistent way in which they unfold. A white dwarf can only support so much mass approximately 1.4 times the mass of our Sun, a limit known as the Chandrasekhar limit, named after the Indian-American astrophysicist Subramanian Chandrasekhar who first calculated it. When the white dwarf approaches this critical mass threshold, either through gradual accumulation of material or through the merger with another white dwarf, something extraordinary happens. The increased pressure triggers a runaway nuclear fusion reaction that consumes much of the star within seconds. Carbon and oxygen atoms in the white dwarf's core fuse into heavier elements, releasing an enormous amount of energy. The star detonates in a thermonuclear explosion of staggering power, briefly shining with the luminosity of several billion suns. This consistent triggering mechanism means that Type Ia supernovae explode with nearly identical energy outputs, making them extraordinarily reliable standard candles. The process of using these cosmic explosions to measure distance began in earnest in the 1990s. Two teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, raced to measure the distances to dozens of remote galaxies using Type Ia supernovae. Their goal was ambitious, to determine whether the expansion of the universe was slowing down due to gravity, as most cosmologists expected. Finding distant supernovae requires a methodical approach. Astronomers must take repeated images of thousands of galaxies, comparing them to identify the sudden appearance of a new light source that wasn't there before. Once a supernova candidate is identified, spectroscopic observations determine whether it is indeed a Type Ia event. If confirmed, astronomers monitor the supernova's brightness over time, tracking how it brightens rapidly and then gradually fades over a period of weeks or months. This light curve, the plot of brightness versus time, provides crucial information. Type Ia supernovae follow a characteristic pattern, reaching peak brightness about 3 weeks after the explosion, and then declining at a predictable rate. By analyzing the shape of this light curve, astronomers can determine the supernova's intrinsic luminosity with remarkable precision. Comparing this intrinsic brightness with how bright the supernova appears from Earth allows them to calculate its distance. The results of these supernova surveys, published in 1998 and 1999, shocked the scientific world. Far from finding that cosmic expansion was slowing down, both teams independently discovered something entirely unexpected. The most distant supernovae appeared dimmer than they should have been if the universe were expanding at a constant or decelerating rate. This could only mean one thing: the expansion of the universe was actually accelerating. This discovery, which earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics, revealed the existence of what we now call dark energy, a mysterious force that counteracts gravity on cosmic scales and pushes the universe apart at an ever-increasing rate. It stands as perhaps the most significant cosmological discovery of our time, and it was made possible by using Type Ia supernovae as cosmic measuring sticks. What makes Type Ia supernovae so powerful as distance indicators is their tremendous luminosity. At peak brightness, a single exploding white dwarf can outshine the billions of stars in its host galaxy. This makes them visible across vast cosmic distances, up to 10 billion light-years away with our current telescopes. They extend our distance measuring capabilities far beyond what Cepheid variables allow, deep into the cosmic past, when the universe was less than half its current age. However, using Type Ia supernovae as standard candles is not without challenges. Despite their overall consistency, these explosions do show some variation in their peak brightness. Astronomers have discovered that brighter supernovae tend to fade more slowly, while dimmer ones fade more quickly. This relationship, known as the Phillips relation after astronomer Mark Phillips, who first described it in 1993, allows researchers to calibrate each supernova based on its light curve shape, substantially improving measurement precision. Another complication arises from interstellar and intergalactic dust, which absorbs and scatters light, making distant supernovae appear dimmer and redder than they actually are. To correct for this effect, astronomers observe supernovae across multiple wavelengths, comparing their color to what is expected for a Type Ia event. Any excess redness indicates dust extinction that must be accounted for in distance calculations. The properties of the host galaxies can also influence supernova characteristics. Supernovae in younger, metal-poor galaxies tend to behave slightly differently from those in older, metal-rich environments. Modern supernova surveys carefully analyze host galaxy properties to correct for these subtle effects. Despite these challenges, Type Ia supernovae have proven remarkably effective as cosmic distance indicators. Large-scale projects such as the Sloan Digital Sky Survey, Supernova Survey, the Supernova Legacy Survey, and the Dark Energy Survey have used hundreds of these explosions to map the expansion history of the universe with unprecedented precision. These measurements have confirmed the reality of dark energy and narrowed down its properties, though its fundamental nature remains one of the greatest unsolved mysteries in physics. The James Webb Space Telescope, with its superior infrared sensitivity, promises to detect Type Ia supernovae at even greater distances, potentially allowing us to observe these explosions from when the universe was less than 1/4 its current age. This will provide crucial data about the early behavior of dark energy and how it has influenced cosmic evolution over billions of years. Type Ia supernovae also serve to calibrate other distance measurement techniques used for the most remote cosmic objects. By establishing reliable distances to galaxies containing both supernova and other distance indicators, astronomers can extend the cosmic distance ladder to the farthest observable reaches of the universe. The story of Type Ia supernovae as cosmic measuring tools illustrates how astronomers often find utility in cataclysm. These destructive stellar explosions, which obliterate entire star systems in seconds, have become essential instruments for understanding the largest scales of cosmic structure and evolution. From violent endings come profound beginnings in our knowledge. It's worth pausing to appreciate the remarkable precision we've achieved in these measurements. The fact that we can determine distances of billions of light years with accuracies of a few percent is a testament to both technological advancement and theoretical understanding. A century ago, astronomers debated whether the Milky Way constituted the entire universe. Today, we measure the deceleration parameter of cosmic expansion and constrain the equation of state of dark energy, concepts that would have been unimaginable to earlier generations of astronomers. This progress has required the development of ever more powerful telescopes and instruments, from the Hubble Space Telescope to massive ground-based observatories equipped with adaptive optics to counteract atmospheric distortion. It has also depended on sophisticated statistical techniques to analyze large datasets and account for various sources of uncertainty. The measurement of cosmic distances using Type Ia supernovae exemplifies the scientific method at its best, combining careful observation, theoretical modeling, and continuous refinement of techniques. When the unexpected acceleration of the universe was first detected, astronomers subjected their findings to intense scrutiny, checking for systematic errors and alternative explanations before concluding that they had indeed discovered something fundamentally new about the cosmos. As we lie beneath the night sky, contemplating these distant explosions, we might reflect on the strange interconnectedness of cosmic phenomena. The same nuclear fusion processes that power our sun are, in their runaway form, responsible for the supernova that allow us to measure the universe. The iron in our blood and the calcium in our bones were forged in supernovae explosions billions of years ago, making us quite literally children of the stars we study. The Type Ia supernovae we use as cosmic lighthouses occurred millions or billions of years ago, their light only now reaching our telescopes. In this sense, astronomy is a form of time travel, allowing us to observe not just distant objects, but the distant past. The light from a supernova 8 billion light-years away began its journey toward Earth when our planet was young and life was just beginning to evolve beyond simple single-celled organisms. Yet even supernovae, for all their brilliance, cannot reveal the entirety of cosmic structure. To map the universe on its largest scales and to understand the dynamics of cosmic expansion more fully, astronomers must turn to other methods. Chief among these is the measurement of cosmic redshift, the stretching of light waves caused by the expansion of space itself. Combined with the Hubble law, redshift measurements provide yet another crucial approach to determining cosmic distances, one that extends to the very limits of the observable universe. As we move further out on the cosmic distance ladder, each rung builds upon those before it. The distances determined by parallax calibrate the Cepheid period luminosity relation. Cepheids in turn calibrate the absolute brightness of Type Ia supernovae, and supernovae help calibrate the redshift distance relation that allows us to map the universe to its observable boundaries. In this way, astronomical knowledge forms an interconnected web, with each measurement technique dependent on and supporting the others. The quest to measure cosmic distances reflects something fundamental about human nature, our desire to understand our place in the vastness of space and time. From the first stargazers who recognize patterns in the night sky to today's astronomers using supernovae to probe the cosmic dawn, we have sought to map our surroundings and comprehend our cosmic context. This pursuit connects us across generations and cultures, a shared human endeavor to chart the universe and our place within it. As we venture beyond the reach of even the brightest standard candles, we enter a realm where distance measurement relies on a fundamental property of the expanding universe itself. This property manifests as a subtle shift in the color of light from distant galaxies, a phenomenon known as redshift. Combined with a relationship discovered by Edwin Hubble in the early 20th century, redshift has become one of astronomy's most powerful tools for cosmic cartography. To understand redshift, we must first consider the nature of light itself. Light travels as waves, with different wavelengths corresponding to different colors. Violet and blue light have shorter wavelengths, while orange and red light have longer wavelengths. When a light source moves away from an observer, these wavelengths get stretched, shifting all colors toward the longer, redder end of the spectrum. This effect, known as Doppler shift, is similar to how the pitch of an ambulance siren drops as it passes by and moves away from you. In the cosmic context, however, something even more fundamental is occurring. According to Einstein's general theory of relativity, space itself can expand or contract. As the universe expands, it stretches the very fabric of space-time. Light waves traveling through this expanding space get stretched as well, their wavelengths becoming longer and thus redder during their journey. This cosmological redshift serves as direct evidence of cosmic expansion and provides a means to measure vast distances. The connection between redshift and distance emerged from the work of several astronomers in the early 20th century. Vesto Slipher, working at Lowell Observatory in Arizona, measured the spectra of what were then called spiral nebulae between 1912 and 1925. He found that most showed a redshift in their spectral lines, indicating they were moving away from the Milky Way. Meanwhile, Edwin Hubble used Cepheid variables to determine the distances to some of these same objects, proving they were separate galaxies far beyond our own. In 1929, Hubble combined his distance measurements with Slipher's velocity data and made a remarkable discovery. The farther away a galaxy was, the faster it appeared to be receding from us. This direct relationship between distance and recession velocity became known as Hubble's law. It can be expressed mathematically as velocity equals Hubble's constant multiplied by distance. The constant in this equation, h0, represents the current rate of cosmic expansion, approximately 70 kilometers per second per megaparsec in modern measurements. Hubble's law provided astronomers with a powerful new technique for determining cosmic distances. By measuring a galaxy's redshift, which is proportional to its recession velocity, they could calculate its distance using the Hubble constant. This method extended the cosmic distance ladder far beyond what was possible with Cepheid variables or even Type Ia supernovae, allowing astronomers to measure distances to the most remote galaxies in the observable universe. The process of measuring redshift begins with spectroscopy, spreading the light from a distant galaxy into its component wavelengths. Galaxies emit and absorb light at specific wavelengths, creating a pattern of bright and dark lines in their spectra that serve as cosmic fingerprints. Common elements like hydrogen, oxygen, and calcium produce distinctive spectral features that astronomers can readily identify. By comparing the observed wavelengths of these spectral lines with their known rest wavelengths measured in laboratories on Earth, astronomers calculate how much the light has been stretched during its journey. This redshift is typically denoted by the symbol Z, with higher values indicating greater distances. A galaxy with Z equals 1 has its light stretched to twice its original wavelength, while a galaxy with Z equals 2 has its light stretched to 3 times its original wavelength, and so on. For relatively nearby galaxies, with redshifts much less than 1, the relationship between redshift and distance is nearly linear, following Hubble's original formulation. But for the most distant galaxies, with redshifts of 1 or greater, the relationship becomes more complex. The expansion rate of the universe has not remained constant throughout cosmic history, changing due to the competing influences of gravitational attraction, which tends to slow expansion, and dark energy, which accelerates it. To account for these changing dynamics, astronomers use sophisticated cosmological models based on Einstein's field equations of general relativity. These models incorporate our best understanding of the universe's composition, including the contributions of ordinary matter, dark matter, and dark energy. By fitting observational data to these models, astronomers can convert redshifts into accurate distances even for the most remote cosmic objects. The largest redshift measured to date belongs to a galaxy observed when the universe was just 300 million years old, less than 3% of its current age. This galaxy has a redshift of approximately 13, meaning its light has been stretched to 14 times its original wavelength during its 13 billion year journey to Earth. Such extreme redshifts push the light from visible wavelengths all the way into the infrared portion of the spectrum, requiring specialized instruments like the James Webb Space Telescope to detect. Redshift measurements have revolutionized our understanding of cosmic structure and evolution. Large-scale redshift surveys, such as the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Euclid mission, have mapped the three-dimensional distribution of hundreds of thousands to millions of galaxies. These surveys reveal that galaxies are not randomly distributed, but instead form a cosmic web of filaments, clusters, and voids shaped by the gravitational influence of dark matter over billions of years. By examining how this large-scale structure has evolved over cosmic time, as revealed by galaxies at different redshifts and thus different distances, astronomers can test theories of cosmic evolution and constrain the properties of dark energy and dark matter. This approach, known as baryon acoustic oscillations, provides an independent check on distance measurements derived from other methods. The relationship between redshift and distance has another profound implication. Because light travels at a finite speed, looking at distant galaxies means looking back in time. A galaxy with a redshift of 1 is seen as it was when the universe was less than half its current age. A galaxy with a redshift of 7 appears as it was just 750 million years after the Big Bang. By studying galaxies across a range of redshifts, astronomers can directly observe cosmic evolution, from the formation of the first stars and galaxies to the complex structures we see today. This time machine aspect of redshift measurement has allowed astronomers to trace the history of star formation throughout cosmic time. We now know that star formation peaked when the universe was about 3 billion years old, corresponding to redshifts between 1 and 3, and has been declining ever since. The causes of this cosmic noon and subsequent decline reveal key insights into galactic evolution and the changing conditions of the universe. Despite its power, the redshift distance method faces certain challenges. The measured redshift of a galaxy includes not only the cosmological component due to cosmic expansion, but also a Doppler component from the galaxy's own motion through space. These peculiar velocities, which can reach thousands of kilometers per second in dense galaxy clusters, introduce uncertainties in distance determinations, particularly for relatively nearby galaxies. To mitigate this effect, astronomers often average measurements over many galaxies in a given region, assuming that peculiar velocities in different directions will roughly cancel out. For individual galaxies, however, this remains a significant source of uncertainty in redshift-based distances. Another limitation arises from our imperfect knowledge of the Hubble constant itself. Different measurement techniques, such as Cepheid calibrated supernovae versus cosmic microwave background observations, currently yield values that differ by about 10%. This tension, as it has come to be known, represents one of the most significant unsolved problems in modern cosmology and directly affects the accuracy of redshift-based distance measurements. Despite these challenges, the redshift method remains indispensable for cosmic cartography on the largest scales. No other technique can measure distances to the most remote galaxies visible from Earth or map the three-dimensional structure of the universe with comparable precision and coverage. The combination of redshift measurements with other distance indicators has allowed astronomers to construct a comprehensive model of cosmic expansion history, from the Big Bang to the present day. The story of redshift measurement exemplifies how seemingly small effects, a subtle shifting of spectral lines, can reveal profound cosmic truths when carefully observed and interpreted. Edwin Hubble's original dataset contained just 24 galaxies, extending to distances of about 6 million light-years. Today, astronomers have measured redshifts for millions of galaxies out to distances of billions of light-years, mapping a volume of space millions of times larger than what Hubble could access. This progress reflects both technological advancement, with ever more sensitive spectrographs and larger telescopes, and conceptual development, with increasingly sophisticated models of cosmic evolution. It illustrates how science builds incrementally on prior knowledge, each generation of astronomers extending the work of their predecessors, while refining and sometimes revolutionizing our understanding of the cosmos. As we lie beneath the night sky, contemplating distant galaxies whose light has journeyed for billions of years to reach our eyes, we might reflect on the remarkable fact that the universe's expansion is inscribed in that light. The stretching of space itself has left its mark on every photon, a cosmic message that we have learned to decode. Through this decoding, we have mapped the universe to its observable limits and traced its evolution from the first galaxies to the complex cosmic web we inhabit today. In our journey through cosmic distance measurement, we have now reached scales where individual stars and even individual galaxies become mere points in a grander cosmic tapestry. Yet even at these immense distances, astronomers continue to refine their measurements, developing new techniques and instruments to probe ever further into space and time. In the following chapters, we will explore additional methods that complement and extend the cosmic distance ladder, providing independent checks on our map of the universe and revealing new aspects of cosmic structure. Between the realm of Cepheid variables and type Ia supernovae and the vast distances measured by redshift lies an intermediate zone where astronomers employ several ingenious techniques to determine cosmic distances. Two particularly powerful methods in this middle range are surface brightness fluctuations and the Tully-Fisher relation. These approaches fill a crucial gap in the cosmic distance ladder, providing independent measurements that help astronomers cross-check and refine their understanding of the universe's scale. Let us begin with surface brightness fluctuations, a technique that extracts distance information from the graininess of a galaxy's appearance. When we observe a nearby galaxy, we can often resolve individual stars, particularly the brightest ones. But as we look at more distant galaxies, individual stars become impossible to distinguish, and the galaxy appears as a smooth, diffuse patch of light. However, this smoothness is not perfect. Galaxies contain stars of varying brightness, from brilliant supergiants to dim red dwarfs, and this variation creates a subtle patchiness or graininess in the galaxy's appearance. The key insight behind the surface brightness fluctuations method is that the degree of this graininess depends directly on the galaxy's distance. Imagine viewing a forest from different distances. Up close, you can distinguish individual trees. From farther away, the forest appears as a textured green carpet, with visible clumps corresponding to clusters of trees. From very far away, the forest looks like a smooth green patch with minimal texture. Similarly, the statistical fluctuations in a galaxy's brightness across its surface decrease in amplitude as distance increases. Developed in the late 1980s by astronomers John Tonry and Donald Schneider, the surface brightness fluctuations technique works particularly well for elliptical galaxies and the central bulges of spiral galaxies. These regions are dominated by older stellar populations with relatively uniform properties, which simplifies the analysis. By carefully measuring the magnitude of brightness fluctuations across a galaxy's image and comparing this to theoretical models of stellar populations, astronomers can determine the galaxy's distance with remarkable precision. The practical implementation of this method requires high-quality images with excellent spatial resolution. Ground-based telescopes, equipped with adaptive optics to correct for atmospheric blurring, or space-based observatories like Hubble, provide the necessary image quality. Sophisticated image processing techniques then separate the intrinsic brightness fluctuations from foreground stars, background galaxies, and instrumental noise. One advantage of the surface brightness fluctuations method is that it can be applied to galaxies that lack Cepheid variables or recent supernovae. This makes it particularly valuable for elliptical galaxies, which contain primarily older stars and rarely host the young, massive stars that become Cepheids or Type II supernovae. Using this technique, astronomers have measured distances to galaxies up to about 300 million light-years away with accuracies of 5 to 10%. Moving from the statistical properties of a galaxy's stellar populations to its rotational dynamics, we encounter another powerful distance measurement technique known as the Tully-Fisher relation. Discovered in the late 1970s by astronomers R. Brent Tully and J. Richard Fisher, this method exploits a remarkable correlation between a spiral galaxy's rotational velocity and its total luminosity. The physical basis for this relationship lies in the dynamics of galactic formation. More massive galaxies contain more stars, making them more luminous, and also rotate faster due to their stronger gravitational fields. This connection between mass, luminosity, and rotation creates a predictable relationship that can be used as a cosmic yardstick. To apply the Tully-Fisher relation, astronomers first measure a spiral galaxy's rotational velocity by observing the Doppler shift of its spectral lines. As a galaxy rotates, the side moving toward us appears slightly blue-shifted, while the receding side appears red-shifted. The difference between these shifts reveals how fast the galaxy is spinning. For many galaxies, this measurement focuses on the 21-centimeter emission line from neutral hydrogen gas, which extends far into the galaxy's outer regions and provides a good indicator of the overall rotation. Once the rotational velocity is determined, astronomers use the Tully-Fisher relation to calculate the galaxy's intrinsic luminosity. By comparing this intrinsic brightness with the galaxy's apparent brightness, they can then determine its distance. Modern applications of this technique achieve accuracies of about 15 to 20%, making it somewhat less precise than Cepheid variables or Type Ia supernovae, but applicable to a wider range of galaxies. Over the years, astronomers have refined the Tully-Fisher relation by exploring which wavelengths of light provide the tightest correlation with rotational velocity. Infrared observations, particularly in the near-infrared bands, have proven especially effective. Infrared light penetrates dust more readily than visible light, giving a clearer view of a galaxy's total stellar content, and thus a more accurate measure of its intrinsic luminosity. A variant of this approach, called the baryonic Tully-Fisher relation, further improves accuracy by accounting for a galaxy's gas content in addition to its stars. This version of the relation works better for smaller, gas-rich galaxies, where a significant fraction of the baryonic or ordinary matter exists as interstellar gas rather than stars. The Tully-Fisher relation has been used to measure distances to thousands of spiral galaxies out to about 700 million light-years. These measurements have helped map the large-scale structure of the nearby universe, revealing the local cosmic web of galaxy clusters, filaments, and voids. They have also contributed to our understanding of peculiar velocities, the motions of galaxies through space beyond the smooth Hubble flow of cosmic expansion. Both surface brightness fluctuations and the Tully-Fisher relation serve as important cross-checks on the cosmic distance ladder. By comparing distance measurements made with different techniques, astronomers can identify and correct for systematic errors in each method. This process of cross-calibration strengthens the overall reliability of cosmic distance measurements and enhances our confidence in the resulting cosmic map. The application of these intermediate range techniques illuminates how astronomers approach the challenge of measuring an object whose distance cannot be directly determined. They look for observable properties that correlate with intrinsic physical characteristics, creating cosmic rulers based on the physics of galactic structure and evolution. This approach exemplifies the ingenuity of astronomical research, finding ways to extract distance information from seemingly unrelated properties like brightness fluctuations or rotational velocities. Several other techniques complement these methods in the intermediate distance range. The Faber-Jackson relation, similar to Tully-Fisher but applied to elliptical galaxies, correlates the velocity dispersion of stars with the galaxy's luminosity. The fundamental plane, a more sophisticated version of Faber-Jackson, incorporates additional parameters like a galaxy's effective radius to improve precision. The tip of the red giant branch method uses the maximum brightness of red giant stars, which reaches a nearly uniform value regardless of a star's mass, as a standard candle. Each of these techniques has its strengths, limitations, and optimal range of application. By combining multiple methods, astronomers build redundancy into the cosmic distance ladder, ensuring that no single systematic error can significantly distort our understanding of cosmic scale. The development of these distance measurement techniques also illustrates how astronomical knowledge progresses. The discovery of empirical relationships like Tully-Fisher often precedes a complete theoretical understanding of why they work. Astronomers first identify useful correlations through observation, and then work to explain them through physical models of galaxy formation and evolution. This interplay between empirical discovery and theoretical explanation drives the advancement of astronomical knowledge. As our understanding of galaxy physics improves, so too does the precision of these distance measurement techniques. Modern surveys with large ground-based telescopes and space observatories like Hubble, Spitzer, and now James Webb continue to refine these methods. Advanced statistical techniques help extract the maximum information from observational data, while computer simulations of galaxy formation provide deeper theoretical insights into the physical relationships underlying these methods. The range of distances accessible through surface brightness fluctuations and the Tully-Fisher relation bridges a crucial gap between the local universe, where individual stars can serve as distance indicators, and the distant cosmos, where only the brightest galaxies and quasars are visible. This intermediate range encompasses numerous galaxy clusters and superclusters, the largest gravitationally bound structures in the universe. Accurate distance measurements in this range are essential for mapping these structures and understanding how they formed and evolved over cosmic time. By combining these intermediate range techniques with Cepheid variables, type Ia supernovae, and redshift measurements, astronomers have constructed a comprehensive three-dimensional map of the observable universe. This map reveals a cosmic web of filaments and voids, with galaxies tracing the underlying distribution of dark matter. The largest structures in this web extend for hundreds of millions of light years, dwarfing individual galaxies and even massive galaxy clusters. The patterns revealed by this mapping effort provide crucial tests for theories of cosmic evolution. The distribution of galaxies in space, their clustering properties, and their peculiar velocities all contain information about the initial conditions of the universe and the forces that have shaped its development over 13.8 billion years. Precise distance measurements form the foundation for these tests, converting the apparent two-dimensional distribution of galaxies on the sky into a true three-dimensional map. As we contemplate these intermediate distance measurement techniques, we might reflect on how they connect the familiar to the unfathomable. The same physical principles that govern the rotation of our Milky Way galaxy apply to distant spirals whose light has traveled for hundreds of millions of years to reach our telescopes. The statistical properties of stellar populations that create brightness fluctuations in nearby elliptical galaxies operate in the same way in galaxies whose light set out when dinosaurs walked the Earth. This continuity of physical law across vast cosmic distances gives us confidence that our astronomical measurements are reliable, even when applied to galaxies so remote that they appear as mere smudges of light, even in our most powerful telescopes. It also reminds us of our profound connection to the cosmos, inhabitants of a universe that operates according to consistent principles across billions of light years and billions of years. Yet even these intermediate range techniques eventually reach their limits. To probe the most distant regions of the observable universe, astronomers must employ yet another set of methods, including one based on the bending of light by gravity itself. This phenomenon, known as gravitational lensing, provides a powerful tool for measuring distances and masses in the far cosmos, revealing aspects of cosmic structure that would otherwise remain hidden from view. Among the many techniques astronomers use to measure cosmic distances, perhaps none is more elegant or directly connected to the fundamental nature of spacetime than gravitational lensing. This phenomenon, predicted by Einstein's general theory of relativity and confirmed through numerous observations, occurs when the gravity of a massive object bends the path of light passing near it. This bending creates distortions, multiple images, and magnifications that astronomers can use to determine distances and masses across the cosmos. To understand gravitational lensing, we must first appreciate how gravity affects the fabric of space-time. According to Einstein, massive objects do not simply attract other objects through a force acting across distance, as in Newton's conception of gravity. Instead, mass causes space-time itself to curve, and this curvature guides the motion of objects, including light. Just as a heavy ball placed on a stretched rubber sheet creates a depression that causes smaller balls to roll toward it, massive cosmic objects create distortions in space-time that bend the paths of light rays passing nearby. This bending of light by gravity was first confirmed during a solar eclipse in 1919, when Arthur Eddington and his colleagues observed that stars positioned near the edge of the Sun appeared slightly shifted from their known positions. The Sun's mass had bent the starlight just as Einstein's theory predicted. This historic observation provided one of the first experimental confirmations of general relativity and hinted at the possibility of more dramatic gravitational lensing effects. It wasn't until 1979, however, that astronomers discovered the first example of strong gravitational lensing beyond our solar system. They observed twin images of a distant quasar, now known as the twin quasar, or Q0957+561, produced when a galaxy along our line of sight bent the quasar's light into multiple paths that reached Earth. Since then, hundreds of gravitational lenses have been discovered, from simple double images to complex configurations like Einstein rings and Einstein crosses. Gravitational lensing occurs in several forms, each providing different types of information about cosmic distances and structures. Strong lensing creates multiple images or arcs when the lens and source are nearly aligned from our perspective. Weak lensing produces subtle distortions in the shapes of background galaxies, detectable only through statistical analysis of many galaxies. Microlensing temporarily brightens a background star when a compact object passes precisely between us and the star, and cosmic shear refers to the accumulated weak lensing effects from the large-scale structure of the universe itself. For distance measurement, strong lensing provides particularly valuable information. When a massive galaxy, or galaxy cluster acts as a lens, creating multiple images of a background source. The geometrical configuration depends on the distances between Earth, the lens, and the source. By carefully modeling the lens system, astronomers can determine these distances, even for extremely remote objects that might otherwise be too faint to study. The time delay technique offers one powerful approach to distance measurement using gravitational lenses. When a distant quasar is lensed into multiple images, the light forming each image follows a different path through space. These paths have different lengths and pass through different regions of the gravitational potential of the lensing galaxy. As a result, variations in the quasar's brightness do not appear simultaneously in all images, but instead show measurable time delays ranging from days to months. These time delays, combined with detailed models of the mass distribution in the lensing galaxy, allow astronomers to calculate what is known as the time delay distance, a combination of distances between Earth, lens, and source. This measurement provides an independent means of determining the Hubble constant, the current expansion rate of the universe. Recent analyses of time delays in several lens systems have yielded values of the Hubble constant with precisions of a few percent, offering an important cross-check on other measurement techniques. Gravitational lensing also serves as a cosmic telescope, magnifying objects that would otherwise be too faint or too small to detect. The gravity of a massive galaxy cluster can amplify the light from background galaxies by factors of 10, 100, or even more. This natural magnification has allowed astronomers to observe galaxies from when the universe was less than 500 million years old, a mere 3% of its current age. By studying these earliest galaxies, scientists gain insights into how the first stars and galaxies formed and evolved. The degree of magnification depends on the alignment between source, lens, and observer. Particularly high magnifications occur along special curves in space called caustics, where the lensing effect becomes mathematically infinite. Objects lying near caustics can be stretched into long, thin arcs, or even into complete or partial rings surrounding the lensing object. These Einstein rings, named after the physicist whose theory predicted them, provide especially constraining data for lens models and distance measurements. Beyond distance measurement, gravitational lensing offers a unique way to map the distribution of matter in the universe, including the invisible dark matter that makes up about 85% of all matter. Because gravity bends light regardless of whether the mass comes from visible or dark matter, lensing responds to the total mass distribution, not just the luminous component. By carefully analyzing lensing effects, astronomers can construct maps of dark matter in galaxy clusters and across larger cosmic structures. Weak gravitational lensing, the subtle distortion of background galaxy shapes by foreground mass, has proven particularly valuable for mapping dark matter on large scales. Although the effect on any individual galaxy is too small to detect reliably, by averaging over millions of galaxies, astronomers can measure the statistical pattern of distortions and infer the underlying mass distribution. Large surveys like the Dark Energy Survey and the upcoming Euclid and Nancy Grace Roman Space Telescope missions apply this technique across large portions of the sky, tracing the cosmic web of dark matter filaments and clusters. This mapping capability makes gravitational lensing a powerful probe of cosmic evolution. By comparing the distribution of dark matter at different distances, corresponding to different epochs in cosmic history, astronomers can track how structure has grown over time under the competing influences of gravity, which tends to enhance cosmic structure, and dark energy, which tends to suppress it. These observations constrain theories of dark energy and test our understanding of how gravity operates on cosmic scales. The practical implementation of gravitational lensing studies requires extraordinary observational precision. To measure weak lensing effects, astronomers must determine the shapes of distant galaxies with accuracies of a few percent, correcting for distortions introduced by telescope optics and Earth's atmosphere. For time delay measurements, they need long-term monitoring campaigns of lensed quasars, often involving coordinated observations from multiple telescopes around the world to ensure continuous coverage. theoretical modeling presents equally significant challenges. To extract distance information from a gravitational lens system, astronomers must model the mass distribution of the lensing galaxy, or cluster, in detail. This requires sophisticated computational techniques that account for both the visible matter in stars and gas, and the invisible dark matter halo surrounding the lens. Uncertainties in these models contribute to the error budget for distance measurements, requiring careful validation through multiple independent analyses. Despite these challenges, gravitational lensing has become an indispensable tool in the modern astronomer's toolkit. It complements other distance measurement techniques, providing independent constraints that help identify and correct for systematic errors. It reveals aspects of cosmic structure that would otherwise remain hidden, particularly the distribution of dark matter. And it allows us to observe objects that would otherwise be beyond the reach of even our most powerful telescopes, extending our cosmic vision to the earliest epochs of galaxy formation. The power of gravitational lensing continues to grow as observational capabilities improve. Adaptive optics systems on large ground-based telescopes can now achieve sharper images than were previously possible, enhancing our ability to study detailed lens configurations. Space telescopes like Hubble and James Webb provide stable, high-resolution imaging free from atmospheric distortions. And large-scale surveys are increasing the number of known lens systems from hundreds to thousands, enabling statistical analyses that average over individual peculiarities. Future facilities promise even greater advances. The Vera C. Rubin Observatory, expected to begin operations in the mid-2020s, will survey the entire visible sky every few nights, discovering thousands of new gravitational lens systems and monitoring their variability. The Nancy Grace Roman Space Telescope will provide Hubble-quality imaging over much wider fields, enabling weak lensing measurements with unprecedented precision. And next-generation, extremely large telescopes with 30-meter or larger primary mirrors will resolve details in lens systems that are currently beyond our reach. The story of gravitational lensing illustrates the profound interconnection between theory and observation in modern astronomy. Einstein's equations predicted the bending of light by gravity decades before technology advanced enough to observe these effects beyond our solar system. Today, these same equations guide our interpretation of complex lens configurations, allowing us to extract information about distances and masses across the cosmos. This dialogue between theoretical physics and observational astronomy continues to deepen our understanding of the universe on its largest scales. As we contemplate the bending of light by the gravitational pull of massive objects, we might reflect on the remarkable nature of the cosmic census we are conducting. Through gravitational lensing and other distance measurement techniques, we are mapping not just the visible universe of stars and galaxies, but also the invisible scaffolding of dark matter that underlies all cosmic structure. We are tracing not just where matter is, but how it has moved and clustered over billions of years under the influence of the mysterious dark energy that permeates space. This comprehensive mapping effort reveals a universe of extraordinary complexity and beauty, a cosmic web of filaments, clusters, and voids shaped by the interplay of gravity and expansion. Our ability to measure the distances to objects across this vast tapestry, from nearby stars to the most distant galaxies, represents one of humanity's greatest scientific achievements, transforming our understanding of our place in the cosmos and the nature of the universe itself. Yet even as our measurement techniques grow more sophisticated and our cosmic maps more detailed, challenges and uncertainties remain. Different methods sometimes yield slightly different results, hinting at either undiscovered systematic errors or potentially new physics beyond our current understanding. These discrepancies, far from being discouraging, drive further innovation and refinement in our approach to cosmic cartography. In the next chapter, we will explore these challenges and the ongoing work to address them, ensuring that our map of the universe rests on the most solid foundation possible. As we have journeyed through the various techniques astronomers use to measure cosmic distances, we have focused primarily on their remarkable successes, how they have enabled us to map the universe across billions of light years and billions of years of cosmic history. But no scientific endeavor, no matter how sophisticated, is without its challenges and uncertainties. In this chapter, we explore the complexities and limitations of cosmic distance measurement, the sources of error that astronomers must contend with, and the ongoing efforts to refine and reconcile different measurement approaches. Perhaps the most significant current challenge in cosmic distance measurement is what has come to be known as the Hubble tension. This refers to a discrepancy between two different ways of measuring the Hubble constant, the parameter that describes the current expansion rate of the universe. Methods that rely on the local, nearby universe, such as Cepheid-calibrated Type Ia supernovae, consistently yield values around 73 kilometers per second per megaparsec. But methods based on the cosmic microwave background radiation, the afterglow of the Big Bang, combined with our understanding of cosmic evolution, yield values closer to 67 kilometers per second per megaparsec. This difference of about 8% might seem small, but it far exceeds the stated uncertainties of either measurement. If both approaches are correct and free from significant systematic errors, this discrepancy could indicate new physics beyond our standard cosmological model, perhaps involving additional types of particles, modified gravity, or dark energy with properties that change over time. Alternatively, it might point to unrecognized systematic errors in one or both measurement techniques. Resolving this tension has become one of the most active areas of research in modern cosmology. The Hubble tension highlights a fundamental challenge in cosmic distance measurement, the need for cross-calibration between different techniques. Each method we have discussed relies on previous rungs of the cosmic distance ladder. Cepheid distances depend on accurate parallax measurements of nearby Cepheids. Type Ia supernova distances are calibrated using Cepheids in galaxies that have hosted these explosions. Redshift distances require an accurate value of the Hubble constant, which itself depends on these other methods. This interconnected nature means that errors at one level propagate through to higher rungs of the ladder. To address this challenge, astronomers pursue multiple independent paths up the cosmic distance ladder. For instance, they calibrate Type Ia supernovae not only with Cepheids, but also with the tip of the red giant branch method, which uses the consistent maximum brightness of red giant stars as a standard candle. By comparing these different calibration paths, they can identify potential systematic errors and work to correct them. Another significant source of uncertainty in distance measurement comes from interstellar and intergalactic dust. As light travels through space, it encounters microscopic dust particles that absorb and scatter certain wavelengths more than others, effectively dimming and reddening the light. This extinction effect can cause distant objects to appear fainter than they actually are, leading to overestimates of their distances. Correcting for dust extinction requires detailed understanding of both the amount and properties of dust along the line of sight. Within our galaxy, astronomers use dust maps based on far infrared emission, which traces the thermal radiation from the dust itself. For extragalactic measurements, they often rely on the colors of standard candles, comparing observed colors to the expected intrinsic colors to estimate reddening. However, dust properties vary between galaxies and even within different regions of the same galaxy, introducing additional uncertainty. The development of infrared astronomy has helped mitigate dust-related errors. Infrared light penetrates dust more effectively than visible light, so observations at wavelengths of 2 to 4 micrometers suffer less from extinction effects. Space telescopes like Spitzer and James Webb, which operate in this wavelength range, have significantly improved the precision of cosmic distance measurements, particularly for objects in dusty regions of the sky. A third major challenge involves selection effects and observational biases. The objects we use as distance indicators, such as Cepheid variables and Type Ia supernovae, are not randomly distributed throughout the universe. We can only detect and measure them under certain conditions, which can introduce subtle biases into our distance measurements. For example, in more distant galaxies, we can only observe the brightest Cepheid variables, potentially skewing our sample towards stars with particular properties. Similarly, our ability to detect and classify type Ia supernovae depends on factors like their host galaxy's brightness and the timing of our observations. If we fail to properly account for these selection effects, we may introduce systematic errors into our distance measurements. Modern astronomical surveys address these biases through careful survey design and sophisticated statistical techniques. By precisely quantifying their selection criteria and sensitivity limits, astronomers can correct for observational biases or limit their analyses to samples where such biases are minimal. Simulations help quantify the impact of various selection effects on distance measurements, ensuring that final results are as unbiased as possible. Even with perfect observations, free from dust extinction and selection biases, intrinsic variations in our cosmic standard candles introduce additional uncertainty. Type Ia supernovae, while remarkably consistent in their maximum brightness, still show variations of about 15% before corrections based on light curve shape and color. Cepheid variables of the same pulsation period can have slightly different luminosities depending on their metal content, or metallicity in astronomical terms. These intrinsic variations limit the precision of individual distance measurements. To overcome this limitation, astronomers increase their sample sizes, averaging over many individual measurements to reduce random errors. Large surveys like the Supernova Legacy Survey and the Dark Energy Survey have observed hundreds of type Ia supernovae across a wide range of distances, allowing for precise statistical analysis. Similarly, studies of Cepheid variables now include thousands of stars across dozens of galaxies, providing a robust foundation for the cosmic distance ladder. Beyond these observational challenges, theoretical uncertainties also affect cosmic distance measurements. Our understanding of stellar physics underlies many distance measurement techniques, from the period luminosity relation of Cepheids to the explosion mechanism of type Ia supernovae. Similarly, our cosmological models, based on Einstein's theory of general relativity, guide our interpretation of redshift measurements and gravitational lensing observations. If these theoretical foundations contain gaps or errors, they could affect the distances we derive. These theoretical uncertainties motivate continuous refinement of both stellar and cosmological models. Advanced computer simulations now allow astronomers to model Cepheid pulsations and supernova explosions in 3 dimensions, capturing complex physical processes that affect their observable properties. Cosmological simulations, tracking the evolution of the universe from shortly after the Big Bang to the present day, help connect observations at different cosmic epochs and test whether our theoretical framework consistently explains the full range of astronomical data. The interplay of these various uncertainties makes cosmic distance measurement a complex, multifaceted problem. No single observation or technique can provide a complete solution. Instead, astronomers employ a diverse array of methods, each with its own strengths and limitations, and look for consistency across different approaches. When discrepancies arise, as in the case of the Hubble tension, they drive further investigation and ultimately deeper understanding. Despite these challenges, it is remarkable how precisely we can measure cosmic distances. The distances to nearby galaxies are now known to within a few percent, while even objects billions of light years away can be located with uncertainties of 10 to 15%. This precision reflects the cumulative effort of generations of astronomers, developing and refining measurement techniques, building more powerful observational tools, and creating more sophisticated analytical methods. The ongoing improvement in distance measurement precision has profound implications for cosmology. More precise measurements allow astronomers to better constrain the properties of dark energy, investigate potential modifications to Einstein's theory of gravity, and test models of cosmic inflation, the theorized period of rapid expansion in the earliest moments of the universe. They also enhance our understanding of galaxy formation and evolution, helping connect observations across different cosmic epochs into a coherent narrative of how the universe has changed over time. Looking toward the future, several developments promise to further enhance the precision of cosmic distance measurements. The Gaia mission continues to refine parallax measurements for stars throughout our galaxy, strengthening the foundation of the cosmic distance ladder. The James Webb Space Telescope, with its unprecedented infrared sensitivity, will detect Cepheid variables and Type Ia supernovae at greater distances than ever before, while minimizing uncertainties due to dust extinction. And next-generation ground-based facilities, like the Extremely Large Telescope and the 30-meter telescope, will provide the spectroscopic capabilities needed to study gravitational lenses and distant supernova in unprecedented detail. Beyond these observational advances, new measurement techniques continue to emerge. Gravitational wave astronomy, inaugurated with the detection of merging black holes in 2015, offers an entirely independent way to measure cosmic distances. When neutron stars merge, they produce both gravitational waves and electromagnetic radiation. By analyzing the gravitational wave signal, astronomers can directly determine the distance to the merger, independent of the cosmic distance ladder. Although still in its early stages, this approach may eventually help resolve tensions in current distance measurements. The history of cosmic distance measurement reveals a pattern of continuous refinement interspersed with occasional revolutionary advances. From Bessel's first stellar parallax measurement to Hubble's discovery of cosmic expansion to the surprising detection of accelerating expansion using Type Ia supernovae, each major breakthrough has transformed our understanding of the universe. Today's challenges, like the Hubble tension, may well lead to the next transformative insight into the nature of space, time, and the cosmos itself. As we contemplate the challenges and uncertainties in measuring cosmic distances, we might reflect on how they exemplify the scientific process at its best. Science progresses not by claiming perfect knowledge, but by rigorously quantifying and reducing uncertainty, by transparently acknowledging limitations, and by following the evidence even when it challenges established ideas. The ongoing effort to refine cosmic distance measurements demonstrates this process in action, showing how astronomers continuously test and improve their understanding of the universe. The quest for more precise cosmic distances also reminds us of the remarkable achievements of modern astronomy. Through patient observation, theoretical insight, and technological innovation, humans have learned to measure distances millions and billions of times greater than anything our ancestors could comprehend. From our vantage point on a small planet orbiting an ordinary star, we have mapped the observable universe across 13.8 billion years of cosmic history. Few accomplishments better demonstrate our species' capacity for understanding the natural world. In the final chapter of our journey, we will look to the future of cosmic distance measurement, exploring upcoming missions and instruments that promise to extend and refine our cosmic yardsticks. These new capabilities will not only address current challenges like the Hubble tension, but may also reveal entirely new aspects of cosmic structure and evolution, continuing humanity's ongoing effort to map the vastness of space and understand our place within it. As we stand at the frontier of astronomical knowledge, gazing out at the vast cosmos mapped through generations of scientific inquiry, we find ourselves not at the end of a journey, but at the beginning of a new era in cosmic cartography. The coming decades promise revolutionary advances in our ability to measure cosmic distances, driven by new observatories, innovative techniques, and computational approaches that were unimaginable just a generation ago. In this final chapter, we explore the future of cosmic distance measurement and how it will transform our understanding of the universe. Perhaps the most anticipated astronomical facility of this decade is the Vera C. Rubin Observatory, currently under construction in Chile. With its 8.4-meter primary mirror and revolutionary 3.2 gigapixel camera, Rubin will conduct the legacy survey of space and time, observing the entire visible southern sky every few nights for 10 years. This unprecedented survey will discover millions of transient events, including countless supernovae, and track the positions and motions of billions of stars and galaxies. For cosmic distance measurement, Rubin's impact will be transformative. It will discover and monitor thousands of Type Ia supernovae each year, far more than all previous surveys combined. This vast sample will allow astronomers to refine their understanding of these cosmic standard candles, identifying subtle subclasses and environmental dependencies that may help resolve the Hubble tension. Similarly, it will detect countless Cepheid variables in nearby galaxies, strengthening this crucial rung of the cosmic distance ladder. Beyond these established methods, Rubin will enable entirely new approaches to distance measurement. Its repeated observations of the same patches of sky will reveal thousands of strongly lensed quasars and supernovae, where multiple images of the same distant object appear due to gravitational lensing by intervening galaxies. By monitoring how brightness variations propagate through these different images, astronomers can measure time delays with unprecedented precision, yielding independent measurements of cosmic expansion. Complementing Rubin's ground-based survey, the Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will bring Hubble-like imaging capabilities to much wider fields of view. With its 2.4-meter mirror and wide-field infrared camera, Roman will survey vast swaths of the sky with resolution and sensitivity previously available only for small targeted observations. Its infrared capabilities will be particularly valuable for cosmic distance measurement, allowing astronomers to see through dust and detect distant standard candles with minimal extinction effects. One of Roman's primary missions will be to conduct a wide-area survey optimized for weak gravitational lensing measurements. By precisely measuring the shapes of billions of galaxies, astronomers will map the distribution of dark matter across cosmic time with extraordinary detail. This three-dimensional map will reveal how cosmic structure has evolved under the competing influences of gravity and dark energy, providing new constraints on the expansion history of the universe, independent of the traditional cosmic distance ladder. Roman will also conduct a dedicated supernova survey, repeatedly observing selected fields to discover and characterize thousands of Type Ia supernovae out to redshifts of about 2, when the universe was less than a third of its current age. The combination of infrared observations, which reduce dust-related uncertainties, stable space-based imaging, which enables precise photometric calibration, and wide field coverage, which increases sample sizes, will make this the definitive supernova dataset for years to come. While Rubin and Roman represent evolutionary advances, building on established observational approaches, the next generation of extremely large telescopes promises truly revolutionary capabilities. 3 such facilities are currently under development: the 30-meter telescope in Hawaii, the giant Magellan telescope in Chile, and the extremely large telescope also in Chile, with a primary mirror spanning an extraordinary 39 meters. These behemoths will collect between 10 and 100 times more light than today's largest optical telescopes, allowing them to observe fainter objects with higher resolution than ever before. For cosmic distance measurement, this translates to the ability to detect and characterize individual stars in galaxies 10 times farther away than is currently possible. Cepheid variables, currently observable only in relatively nearby galaxies, will be detectable throughout the local group and beyond, while the tip of the red giant branch method can be applied to galaxies 10 times more distant than today's limit. The increased sensitivity and spectral resolution of these telescopes will also revolutionize gravitational lensing studies. They will resolve details in lensed images that remain blurred in current observations, revealing the fine structure of both the lensing galaxies and the lensed sources. This enhanced resolution will enable more precise modeling of lens systems, reducing uncertainties in the derived distances and in measurements of the Hubble constant based on time delays. In space, the James Webb Space Telescope, launched in 2021, represents the most advanced infrared observatory ever built. Its 6.5-meter segmented mirror, operating at temperatures below 50 Kelvin, provides unprecedented sensitivity in the near and mid-infrared. This opens new windows for cosmic distance measurement, particularly for highly redshifted objects, whose light has been stretched from visible wavelengths into the infrared by cosmic expansion. Webb's infrared capabilities allow it to detect Cepheid variables and Type Ia supernovae in dusty environments where they would be obscured at visible wavelengths. This reduces systematic uncertainties related to dust extinction, one of the primary sources of error in the cosmic distance ladder. Webb can also observe standard candles in more distant galaxies than previously possible, extending direct distance measurements farther across the cosmic web. Perhaps most excitingly, Webb can observe the earliest galaxies that formed in the universe, when it was less than 5% of its current age. By studying these primordial systems, astronomers can trace how galaxy formation proceeded in the early cosmos and connect these observations to the later universe revealed by other facilities. This provides a more complete picture of cosmic evolution across all epochs, constraining cosmological models and the properties of dark energy and dark matter. Moving beyond the traditional electromagnetic spectrum, gravitational wave astronomy offers an entirely new approach to measuring cosmic distances. When compact objects like neutron stars merge, they generate both gravitational waves, ripples in the fabric of space-time, and electromagnetic radiation across multiple wavelengths. The gravitational wave signal directly encodes the distance to the source, independent of the cosmic distance ladder, while the electromagnetic counterpart provides the redshift. Together, these observations yield what astronomers call standard sirens, gravitational wave events whose distance and redshift are known independently. As gravitational wave detectors like advanced LIGO, Virgo, and CAGRA improve in sensitivity, and as next-generation facilities like the Einstein Telescope and Cosmic Explorer come online in the 2030s, the number of detected neutron star mergers will increase from a trickle to a flood. This will provide an entirely independent measurement of the Hubble constant and cosmic expansion history, potentially resolving the current Hubble tension. Even more ambitious is the Laser Interferometer Space Antenna, or LISA, a space-based gravitational wave observatory scheduled for launch in the 2030s. With detector arms millions of kilometers long, LISA will be sensitive to lower frequency gravitational waves than ground-based facilities, allowing it to observe the mergers of supermassive black holes at the centers of galaxies. These events, visible across cosmic time, will serve as standard sirens for mapping the expansion history of the universe from its earliest epochs to the present day. The future of cosmic distance measurement also lies in computational advances and data science techniques. The datasets generated by facilities like Rubin, Roman, and the extremely large telescopes will be enormous, containing petabytes of information that must be processed, analyzed, and interpreted. Machine learning algorithms will scan these vast datasets for patterns and correlations that might escape human notice, potentially revealing new distance indicators or refining existing ones. Sophisticated statistical techniques will combine information from multiple measurement methods, properly accounting for correlations and systematic uncertainties. This approach, known as joint inference, extracts the maximum information from diverse datasets, producing more precise and robust distance measurements than any single method alone. Similarly, hierarchical Bayesian analysis allows astronomers to model the entire cosmic distance ladder simultaneously, rigorously propagating uncertainties from one rung to the next. Computational advances also enable more detailed theoretical modeling of the objects used as distance indicators. Three-dimensional simulations of Cepheid pulsations, incorporating the complex interplay of radiation, convection, and magnetic fields, help astronomers understand the subtle dependencies of the period-luminosity relation on stellar properties like mass, age, and chemical composition. Similarly, sophisticated models of Type Ia supernova explosions, tracking nuclear reactions and radiation transport through the expanding debris, improve our understanding of these crucial cosmic beacons. On the largest scales, cosmological simulations trace the evolution of the universe from the primordial fluctuations seen in the cosmic microwave background to the complex cosmic web observed today. By comparing these simulations with observational data at multiple epochs, astronomers test whether our cosmological models consistently explain the full range of astronomical observations, from the early universe probed by the microwave background to the recent cosmos mapped through supernovae and gravitational lensing. As these various observational and computational approaches mature, astronomers anticipate significant progress on key questions in cosmology. The Hubble tension may be resolved through improved calibration of the cosmic distance ladder, the discovery of systematic effects not currently accounted for, or the revelation of new physics beyond the standard cosmological model. The properties of dark energy may be constrained with sufficient precision to distinguish between a cosmological constant, as Einstein initially proposed, and more exotic models where dark energy evolves over cosmic time. Beyond these specific questions, the enhanced precision of cosmic distance measurements will reveal the detailed structure and dynamics of the nearby universe with unprecedented clarity. The three-dimensional motions of nearby galaxies, influenced by both the smooth Hubble flow of cosmic expansion and local gravitational attractions, encode information about the distribution of dark matter and the formation history of our cosmic neighborhood. More precise distance measurements will allow astronomers to separate these various components and reconstruct the full dynamical history of our local cosmic web. At the other extreme, improved distance measurements for the most remote objects will sharpen our view of the early universe, revealing how the first stars and galaxies emerged from the primordial darkness and began the process of cosmic enrichment that ultimately led to planets, life, and consciousness. By connecting observations across cosmic time through a reliable distance scale, astronomers can trace the complete arc of cosmic evolution from its earliest moments to the present day. As we contemplate these future advances, we might reflect on how far our understanding has come and how much remains to be discovered. A century ago, astronomers debated whether the Milky Way constituted the entire universe. Today, we map billions of galaxies across cosmic time and measure the expansion rate of the universe with percent-level precision. Yet fundamental questions remain about the nature of dark matter and dark energy, the physics of the earliest moments after the Big Bang, and the ultimate fate of the cosmos. The quest to measure cosmic distances reflects something profound about human nature, our desire to locate ourselves in the vastness of space and time, to understand our cosmic context and origins. From the first stargazers who tracked celestial motions to today's astronomers using gravitational waves to measure cosmic expansion, we have sought to map our surroundings with ever greater precision and scope. This ongoing endeavor connects us across generations and cultures, a shared human project to comprehend the universe and our place within it. As we develop new instruments and techniques, pushing the boundaries of what can be measured and understood, we continue this ancient quest, reaching ever further into the cosmic ocean and deepening our appreciation for the extraordinary universe we call home. In the quiet hours of the night, as we gaze at the stars scattered across the darkness, we can now appreciate not just their beauty, but also their distance, their history, and their connection to our own existence. Through the patient work of countless astronomers, the development of ingenious measurement techniques, and the creation of ever more powerful observational tools, we have learned to measure the immeasurable and comprehend the incomprehensible, transforming the night sky from a mysterious backdrop to a mapped and understood cosmic landscape. And yet, with each advancement, new questions emerge, ensuring that our journey of cosmic exploration continues, as boundless as the universe itself. The story of cosmic distance measurement is, in many ways, the story of human perspective expanding outward in concentric circles of understanding. For most of human history, our world seemed vast, and the heavens appeared as a celestial dome not far above. The realization that Earth orbits the Sun, that the Sun is one star among billions in the Milky Way, and that the Milky Way is one galaxy among billions in the observable universe, each represented a profound shift in our cosmic perspective, a redrawing of the map with ourselves placed in an increasingly humble position. Yet there is another way to view this journey, not as a story of diminishment, but as one of remarkable connection. The same physical laws that govern the pulsations of Cepheid variables in distant galaxies operate in our own stellar neighborhood. The light that carries the spectral fingerprints of elements in remote quasars follows the same principles as the light that illuminates our world. The cosmic expansion that stretches wavelengths from galaxies billions of light years away connects us to the earliest moments of the universe, to the same primordial soup from which all structure eventually emerged. In measuring cosmic distances, we have discovered that we are part of an interconnected cosmic web that spans billions of light years and billions of years. The elements that form our bodies were forged in stellar furnaces and scattered through space by supernova explosions, the very same phenomena we now use as standard candles to measure the universe. Our planet orbits a star that formed from the recycled debris of earlier stellar generations in a galaxy that has evolved through interactions with its cosmic environment over billions of years. The precision with which we can now chart these vast distances speaks to something remarkable about human cognition. From our vantage point on a small rocky planet, using instruments built from materials found on that planet and theories constructed by minds evolved to navigate terrestrial landscapes, we have managed to measure distances millions and billions of times greater than anything our species directly experiences. The ability to conceptualize such scales, to develop methods to measure them, and to build models that explain observations across cosmic time represents a profound achievement of the human intellect. This achievement has not come easily or straightforwardly. The history of cosmic distance measurement is filled with controversies and corrections, with techniques refined over decades and uncertainties gradually reduced through persistent effort. Each generation of astronomers has built upon the work of their predecessors, developing new methods and instruments to push the boundaries of the measurable universe ever outward. The current challenges, like the Hubble tension, remind us that this process continues, that science advances not through sudden perfect knowledge, but through the patient resolution of discrepancies and the continuous refinement of understanding. As we have seen, the quest to measure cosmic distances has driven technological innovation, from the development of ever larger and more sophisticated telescopes to the launch of space-based observatories that transcend the limitations of our atmosphere. It has spurred theoretical advances, from Einstein's general theory of relativity, which explains how gravity bends light, to detailed models of stellar evolution that allow us to understand the physics of cosmic standard candles. And it has inspired new computational approaches, from the processing of vast astronomical datasets to the simulation of cosmic evolution across billions of years. The practical implications of these measurements extend far beyond astronomy. The same GPS technology that uses precise timing to determine positions on Earth incorporates corrections from Einstein's theories, developed to explain the bending of starlight by gravity. The image processing algorithms refined for astronomical observations find applications in medical imaging and remote sensing. And the collaborative international efforts that characterize modern astronomical research provide a model for addressing other global challenges. Perhaps most profoundly, accurate cosmic distance measurements have transformed our understanding of cosmic history and possibly our cosmic future. We now know that the universe is about 13.8 billion years old, that it has expanded from an incredibly hot, dense initial state, and that this expansion is currently accelerating under the influence of dark energy. These discoveries have philosophical and even spiritual implications, changing how we conceptualize our place in the cosmic story and what might lie ahead for the universe as a whole. The accelerating expansion revealed by Type Ia supernova measurements suggests that the universe will continue to expand forever, with galaxies beyond our local group eventually receding so rapidly that they disappear from view. Future civilizations, should they exist, might observe a much emptier cosmic sky than we do, with even the evidence for the Big Bang and cosmic evolution fading from observational accessibility. Our era, with its rich view of the cosmic past and the ability to reconstruct the full arc of cosmic history, may represent a special window of opportunity for understanding the universe. This perspective lends a certain poignancy to our current astronomical endeavors. The knowledge we are accumulating now, the measurements we are making of distant galaxies and the early universe, may represent a unique cosmic legacy, insights that might not be accessible to observers in the far future. This adds urgency to our efforts to map the cosmos and understand its evolution, to take full advantage of our fortunate cosmic timing. As we continue to refine our measurements and extend our cosmic vision with new facilities like the Vera C. Rubin Observatory, the James Webb Space Telescope, and eventually gravitational wave observatories like LISA, we can anticipate new surprises and discoveries. The universe has repeatedly proven to be more strange and wonderful than our theories predicted, from the unexpected acceleration of cosmic expansion to the ubiquity of exoplanets around other stars. Each improvement in measurement precision and each extension of observational reach brings the possibility of new revelations about the cosmos and our place within it. In the quiet darkness of night, as we gaze at the stars and contemplate the immensity of space, we can now appreciate that what appears as a random scattering of lights is in fact a carefully mapped landscape with measured distances and understood physical processes. The light from a distant galaxy, traveling for millions or billions of years before reaching our telescopes, carries within it the story of cosmic evolution and the imprint of cosmic expansion. Our ability to interpret this light, to measure the distance to its source, and to place it within a comprehensive model of the universe represents one of humanity's greatest intellectual achievements. Yet, for all our knowledge, a sense of wonder remains. The fact that we can measure distances to galaxies billions of light years away does not diminish their mystery, but enhances it, giving us a more profound appreciation for the scale and complexity of the cosmos. The discovery that dark energy drives the accelerating expansion of space does not close the book on cosmic understanding, but opens new chapters filled with questions about the fundamental nature of reality. As you drift towards sleep beneath this mapped yet still mysterious cosmic canopy, consider that the light reaching your eyes has journeyed across distances we have learned to measure but can scarcely comprehend. The atoms that form your body and the planet beneath you were forged in the same stellar processes that create the standard candles we use to measure cosmic distances. And the human curiosity that drives us to map the cosmos, to measure the immeasurable, connects us across generations in a shared quest to understand the universe and our place within it. In every measurement, in every extension of the cosmic distance ladder, in every refinement of our understanding, we find not just knowledge but context, not just facts but meaning. For in learning how to measure the universe, we have also learned something profound about ourselves, a species of cosmic explorers with the remarkable ability to comprehend the vastness in which we dwell, to map our cosmic neighborhood across billions of light years, and to recognize our kinship with the distant stars. Rest now, knowing that even as you sleep, the cosmos continues its stately expansion, carrying within it the atoms, the energy, and the consciousness that make such knowing possible.